All right, welcome back. Here we go with part 2 of the tutorial. Let's share screen. Okay, so this is where we left off last time. So what we will do now is quickly have a look at some FEA results and see how they compare with what we've got so far. All right, so let's skip to the next page. All right, so in the textbook, they've done an FEA result as well. So let's say you do the basic thing in SOLIDWORKS, make your model. Should only take you 5 or 10 minutes to make a model of that. And then once you go into SOLIDWORKS simulation, pretty easy to then set up some constraints and loads. So at this end, at this far end here of the rod, we're just going to fix all degrees of freedom. So that's equivalent to being, rigidly welded to this back plate or something like that. Right? So we're just saying that at this cylindric, circular face on the back here, can't move. Right? And then out here at the end of the rectangular bar, we've got our load applied. Okay, so for this part of the FEA, I've just copied what they've done in the textbook in terms of the loads. So I've just used the imperial units. Right? And if you just press run on SOLIDWORKS, this is the output that you get. Right? And the output is, the default output is this thing von Mises. Right? So as an engineer making use of FEA, you need to know what this is if you're going to use it. Right? I've seen many students just use this without really knowing what it is. Sometimes you can do that. Basically, it's a measure of stress that you use to compare with the yield strength as measured in a tensile test. Okay, so you can kind of use it superficially and not get into too much trouble, but really, as an engineer, you should properly understand what this is, and we'll go through what it is a bit later on. And this is why it's the default output, right? Because you can compare this von Mises stress directly with the yield strength, right? Even though you might have stress components all over the place, it's a complex shape, you can make this simple direct comparison. Right, the other thing to notice that is different to what is presented in the textbook is that Mott has this thing SX as an output. What do you think that might be? And why has this output been used in the presentation from Mott? Okay, and how do we get our output in SOLIDWORKS to look like what they've got in the Mott example? So in my next page here, if you're using SOLIDWORKS, then you just go into edit definition for your stress output and you can select SX, and it tells you that SX is the normal stress in the X direction. Now remember what we said in our previous analysis, we said that the normal stress was in the Y direction. So why has SX been used? What's different between the SOLIDWORKS model or the FEA analysis, or the FE analysis, and the theoretical analysis? The answer is the coordinate system. Okay, so our output from SOLIDWORKS in our FEA, the x-axis is aligned along the length of this rectangular bar. So the correct output to use here is the stress in the X direction if you're using the default coordinate system. So if you had chosen Y normal stress, because that's what we got in our theoretical calculation, you would have got 0 for the stresses. Just another point to note, the use of inappropriate number of significant figures here. And I've just copied that just so that we can compare the results from the picture in the textbook with my analysis results from SOLIDWORKS. Okay. Okay. Right, so I've already answered that. Theoretical stress component is determined in the y direction. What's going on? I already answered that, and we already talked about it. So we already came up with the fact that there are different coordinate systems being used. Okay, so the other thing to note down in the bottom left-hand corner here, the red lines just come up. I've just highlighted in the textbook, it says this model verifies the observation that the highest stress is at element A. Now, they haven't been very consistent in what element A is here, right? So firstly, the diagram wasn't clear to start with. Element A, we presume, is directly above the center of the cylinder here, at the top of the rectangular bar, at the midline, down the length of the bar, right? And now element A is kind of being pointed out somewhere different, right? And if you look at where the max is on mine, it's not quite where they're saying it is. So let's investigate a little bit more. Right, so if we rotate the model around, which we can easily do in SOLIDWORKS, we'll see that the maximum stress that is being indicated here by SOLIDWORKS is not at element A at all. Right? It's down here at the junction between the rod, cylindrical rod, and the rectangular bar. Okay. Right, so I already said that about the location's not quite the same. So let's investigate a little bit more. So what I've done in my model is to use split lines. If you don't know about split lines, you can look those up. I can't remember if I showed you how to do this in my little video or not. But once you know about split lines, it's pretty easy to find on YouTube, short videos on how to create them, right? And they're really useful for splitting up the geometry so you can get accurate outputs of your stresses. All right, so what I've done here is to choose some points. So the first one here that we look at is this node 17. And this is element A according to this diagram here, okay? Aligned with the top of, right, so if you draw this line on the top of the cylinder here, come up, directly up along the back side of the rectangular bar and then across the top, and then where that line intersects with the longitudinal line down the middle of that top face, we get this point here, okay? So according to this original diagram, that's where they're referring to element A, okay? So if we look there, element A for node 17, we get 89 megapascals, very much less than we got for theoretical calculations, right? We got 200 megapascals. And if we look at the maximum now converted to megapascals, so on the previous slide we had still in imperial units, now just converted it to SI units, we get 225 megapascals somewhere other than at element A. And then the next point that I've got here, so from our using our split lines, is a point a short distance away. Okay. I said that here. Yep, so I've done that. Right, so got to here. So a short distance away, as soon as someone says short or long or close or far, right, you need to quantify that. And the way I quantify short in this case is by understanding St. Venant's principle and how at so like one depth away or 10% of the length of the beam away from where something odd is going on, then the stresses return to how they would be, or how, the stresses are as they would be independent of what's happening here. Okay, so instead of it being connected to a cylindrical rod here, if we just chop this off at 300 millimeters, so it looks just like that. If you look at my little picture of me off to the side, in mechanics of solids, applied mechanics and design A, we had drawing of a beam looked like this. We put a force on here, said what's the stress? Okay, so at a distance about a tenth of the length away or a depth away from the end here, doesn't matter whether we have it as a fixed connection or whether it's connected to a cylinder like this. Okay. Yeah, I think there might be a video in week O about St. Venant's principle that you can go where I explain that a bit better. Anyway, so that's what we've done. Look at the stress 30 millimeters away from what was defined as point A or element A. And we've got a stress there of 180 megapascals. So let's calculate theoretically the stress that we get at that point and see how that compares. So have a go at doing that for yourself. Stop the video. All right. How did you go with calculating that theoretically? So I've just done another picture there to show that. So theoretically, stress 30 millimeters away from element A, we can just do 0.9 times 200 because it's, well, why do you think I can do that? Right? How does the stress vary along the length? Varies linearly, so I can just do a simple ratio, right, to get the stress at that point. Or you can go back to your bending moment equation. So at a point here, looking over at the top left-hand side here where my cursor is, right, if we now take the cut at a distance 270 from F, the bending moment is F times 270, right? Or F times 300 minus 30. And we'll get an answer of 180 megapascals. So now we are actually getting correlation between theory and our SolidWorks simulation finite element analysis. Okay. And just a note here that I've now made use of a more appropriate number of significant figures. In fact, I've got 1 decimal place, and 2 to 4 significant figures. Anyway. Right, so let's move on to transverse shear. So still looking at the rectangular bar here, what's the formula for calculating the transverse shear stress due to bending? Okay. Anyone remember? Hopefully you've been able to look it up if you don't remember, and you found the equation BQ upon IT. So you may remember, oh yeah, I remember seeing that back in Applied Mechanics and Design A. So again, fairly easy to look that up, but we now need to be able to interpret and use this correctly. So first thing, V is the internal shear force. So again, take a cut somewhere along the length, work out the shear force as a function of the position along the beam, draw your shear force diagram. Okay, so for this problem, we've just got an end load supported at the other end, so it's essentially a cantilever. The shear force is constant along the length. All right, then we've got Q and I and T. So I probably assume it's the same as we had before, which would be correct. So that's our moment of inertia. And T is the thickness of, or the width of the beam. Might be correct. What about Q? All right, so let's, firstly, where will the maximum stress be along the length of the beam? So firstly, V, well, that's constant along the length, so don't have to worry about that. The cross-sectional moment of inertia, that's the same all the way along the length, doesn't change. That cross-sectional area stays the same. Width or thickness of the beam, that stays the same. Q, not too sure about what that is. So yeah, I've just done put the formulae there and the equations, equilibrium for the shear force. Now, Q, what is this Q? Now, Q is, what do you think it is? Stop the video, go and look it up, whatever. All right, so that's the first moment of area of the area above the layer where you're wanting to know the shear stress. Okay, so the formula for that is AY bar. If you look it up, that's probably what you'll find. But for the axes that we're using here, it will be AZ bar. Okay. Now, what's this bar on top of the Y and the Z mean? We'll get to that in a second. All right, so if we've got our cross section here and we want to know the shear stress, so this transverse shear that we've got here, right, looking at me in the picture, right, if we push down here, we get, it's floppy, right? Because the pages are sliding relative to each other. If I open every page and sprayed some contact adhesive there and I glued all those pages together, what's going to happen when I push here? It's not going to be flop down like that, is it? Right? It's going to be stiff and resist that load. Okay, so what's happening is that we're developing shear stresses in the glue between each page. Yeah, and that stress that we're developing in the glue between each page along the length of the beam is the transverse shear stress. Okay. All right. So here I've just chosen some arbitrary, on the right hand side of the PowerPoint, we've just got some arbitrary location through the depth of the beam. And the shear stress at that location is VQ upon IT, and the Q is AY bar or AZ bar. So it's the area times the distance from the neutral axis to the centroid of this little area above the layer where we want to know the shear stress. Okay, so where is the shear stress going to be maximum? At the top or the bottom? Or at the top or at the neutral axis? Stop the video and answer for yourself. Okay. So if we continue moving this line up, right, Z bar gets bigger and bigger, but A gets smaller and smaller, right? Until we get to a point where A is 0. Okay, so at the top, right, we've essentially got we've got a free surface on the top of the beam, right? So the shear stress there, right, there's no page on top here wanting to slide relative to the outside cover of the book. Right? So the shear stress on the top is 0. Right? And as we come down, the area gets bigger and bigger. Z gets a bit smaller, right? But the first moment of area is maximum when we have this shear plane at the neutral axis, okay, when A is the biggest. So the maximum shear stress or maximum transverse shear is at the neutral axis. All right, so now that we've done that, we can put in some values. So the area here at the neutral axis is T times H over 2. And the distance from the neutral axis to the centroid of this bit of area is H over 4. All right, I, what's that? That's the same as we had last time because it's this transverse shear comes from bending. And we're bending about the x-axis, same cross-sectional area, so the same as we got before. And the T here is the width, turn around, right? The width that we're looking at here of our beam. So we're pushing down on our beam to get the shear along this way. The other dimension that gives us the stress, shear stress, is that width or thickness of the beam. Okay, so in this case it's 10. Now here T and T on the diagram are the same things, but they may not be, right? Same as we had before, right? People have made the mistake in the bending equations to calculate the moment of inertia, BH cubed upon 12. They saw a B here and put that number into the equation, right? Be careful doing that, right? Make sure you understand what these terms mean. All right, so maximum shear stress as at the neutral axis, as I said, and we can put the numbers in now and we get shear stress is 5 megapascals. Can you draw now the stress element? Now this is a bit tricky. So start with the square. Even though this transverse shear, I've talked about it being along the length, now you can probably go back and think about it more along the lines of direct shear. So we've got this force pushing down here. If we draw a little, so this square here represents a point here. Right? And if we have this V on either side of this little square, what directions are those stresses going to be? We've got the same axes as before because we're looking from the side. So we've got Y and Z. Right, we've got this force pushing down here. Right, so we're going to get the shear stress in that direction on that side of the element. Okay. And then because it's in equilibrium, the whole point or the whole square must be in equilibrium. So we've got shear stress going upwards on the back side of this, or the left side of this stress element. And then, because this has to be in equilibrium, we've got some of the forces in the vertical direction equal 0. So it's in equilibrium according to forces. But if we took moments about the center here or any other point, doesn't matter where, we can see that we've got an unbalanced moment, right? So this force on the left is causing clockwise moment about this point, and the shear force or the shear stress on the right-hand side is also causing a clockwise moment. Right? So we need our transverse shear, or a complementary shear rather, going along the length. So this one needs to be going anti-clockwise to balance out the clockwise moments caused by the vertical forces. Okay, so that's our complete state of stress. And these horizontal ones, right, are those stresses in the gluing the pages together that I talked about before. Okay, and then we label the stress element with our label here. So this tau YZ. So the first subscript Y represents the normal to the surface that we're looking at, or normal to the plane that the shear is acting on. And the second subscript is the direction that it's going. Okay, so this one on the right-hand side here is on the Y face going in the Z direction. All right, so let's see if we can get our results from our SolidWorks simulation to compare. So my animations are a bit messed up here. Sorry about that. So we've got, let's see, if we go to the SolidWorks simulation and go to our edit definition, we need to choose from here the correct shear stress. Okay, so we need to know this tau YZ, tau XY, whatever, in order to choose the correct one. Okay? And if you don't know what the shear stresses should look like, then it's going to be very difficult to choose the correct one. Right? So according to our analysis here, we got the YZ plane, but in the SolidWorks coordinate system, it's the XY plane. Right? So that's going to make things a bit difficult. Okay, I've just included in the slides here some notes about whether the shear stress is positive or negative. Unfortunately, the MOT textbook uses a sign convention that's different to what the efficient engineer uses, and also probably different to what you may do in applied mechanics and design B if you do or have done that subject already. Anyway, not going to get into that too much now. Both ways end up with the same, or end up with the correct answer. But yeah, that's going to take me half an hour or so to go through all of that. Best, I think, if we leave it to the example when I get to it, and I'll show you how I make use of the sign convention as is presented in the efficient engineer video that you hopefully would have seen already, and also what if you've got the Hibbler or Beer and Johnson Mechanics of Solids, Mechanics of Materials textbook, it's consistent with that. Anyway, let's go on further. Just looking at the time here, need to stop this little video. What I want to point out firstly is the results that you get from FEA. So if you choose the XY shear stresses, you'll see maximum and minimum big values, way bigger than we calculated, right? These are actually fictitious, meaningless values, right? You can't use them, right? They're an artifact of the way we've modeled this in SolidWorks or any other FEA package, doesn't matter, right? Whatever FEA software you use will give you similar fictitious, meaningless results like this for that location. Everywhere else is green, so it's hard to determine what's going on elsewhere. So you can use the clipping option in SolidWorks. I'm not going to go through that. I've shown you that's there. You can explore that yourself. All right, so now if we use that clipping option, we can see that we've now got uniform or constant shear stress along the length using tau XY to be consistent with the coordinate system in SolidWorks rather than the coordinate system that we used in our theoretical calculations. So you get a value of 5, and note that it's negative, right? So in the previous slide, I said I say that the shear stress is negative. SolidWorks agrees with me. Not that that makes me right, but just, yeah. Anyway, so yeah, so shear stress mostly uniform along the length there, corresponding to what we, closely corresponding to what we had theoretically. And one, let me just, okay. So before we finish off here, just the last thing about fictitious meaningless values in FEA results. So I've gone back to here the von Mises stresses that we talked about before. So I've got 3 different results. So these 2 here on the left are the same, and then they've got 2 different ones here. But right, these all 3 results come from models that have the same geometry, have the same exact geometry that we looked at before, the lengths and dimensions that we have looked at previously, same dimensions. I haven't changed the materials. I've applied the same loads to all 3 models. So the same value of load here, I've applied it in exactly the same way, same constraints at the end or fixtures at the end, all exactly the same for these 3 models here. But yet I've got different results. Why do you think, or how do you think those different results came about? Okay, so if you've stopped the video and had a thought about it, that's good. But what's different is the size of the elements or the numbers of degrees of freedom in my models. Okay, so if you're using SolidWorks and you're creating the mesh for the finite element model, you'll know that there's a slider and there's the default setting, and then there's coarse, and then there's fine. Right? So they shouldn't, if you want your results to be meaningful, the size of the element or the numbers of degrees of freedom, as you decrease the size of the element, increase the numbers of element, increase the degrees of freedom, you should see the results start to not change. Okay, so that you can be confident that, hang on, doesn't matter from a certain point on, in terms of the numbers of degrees of freedom or numbers of elements, my results don't change very much. Right, so you're confident that your results aren't affected by how you've chosen to mesh the model. Okay, right, but here it does. Right, so that's showing you that these numbers are entirely meaningless, fictitious values. You can't use them, right? Because you can get almost any number you want, depending on how many elements you choose. Right? And the reason for that in this case is that we have an internal square corner here, and theoretically, the stress at an internal square corner is infinite. Right? So what you're doing by increasing the number of elements, making them smaller and smaller, is chasing infinity. Right? And you're obviously never going to get there. So don't make the mistake of just using this value as presented by SolidWorks or any other finite element software for that matter, and think this means something. All right, I'm going to stop the video again and come back to this in the next part of the video.